Until 2019, the system that transmitted launch orders for America's nuclear missiles ran on 8-inch floppy disks and IBM hardware from the 1970s. The world saw a punchline, but that architecture had no internet connection, no wireless interface, and no remote attack surface by design. The real question was never why the Pentagon kept using floppy disks. It was whether replacing them would actually make the arsenal safer. In 1968, the Strategic Automated Command and Control System, called SACCS, went live as the backbone for America's land-based nuclear deterrent. Its mission was clear: deliver presidential launch orders to Minuteman III missile crews instantly and without fail. 8 years later, the Air Force brought in the IBM Series 1 minicomputer. This upgrade, finalized in 1976, replaced earlier prototypes with hardware that would remain at the heart of the system for more than 4 decades. The Series 1 was never designed for the consumer market. It ran on discrete logic, with no microprocessor, no commercial operating system, and no network ports. Each machine handled between 32 and 64 kilobytes of memory, enough to process launch codes, but a fraction of what a basic calculator holds today. Data traveled not through wireless signals or the internet, but over dedicated copper landlines, connecting command posts at F.E. Warren in Wyoming, Malmstrom in Montana, and Minot in North Dakota. These 3 missile wings together oversaw hundreds of silos spread across the northern plains. Every launch order, every critical message was stored and transmitted using 8-inch magnetic floppy disks. Each disk held about 80 kilobytes, less than a single photo from a modern smartphone. Yet in the words of a former Air Force engineer, this system was built for reliability, not for speed. A sustainment official recalls, "We were still loading these disks in 2014. People laughed, but they never saw the logic behind it." An analyst adds, "From a cybersecurity standpoint, the absence of modern features was the feature." By anchoring the command chain in hardware and practices that predated the networked era, SACCS created a paradox, a system that looked obsolete but was built to survive threats its designers could barely imagine. The next question is whether that engineering logic held up under scrutiny. Physical isolation, not digital cleverness, formed the backbone of SACCS security. The IBM Series 1 sat alone, no Ethernet, no wireless, no serial over IP adapters, shielded from any outside network. Every signal traveled through copper landlines, routed in hardened conduits, with no pathway for remote intrusion. This air gap wasn't a matter of neglect. It was a deliberate barrier, designed to make sure that only someone physically present, with the right credentials and media, could interact with the system at all. The storage media followed the same philosophy. Each 8-inch floppy disk was a blank slate of magnetically encoded data, with no embedded firmware, no hidden microcontroller, and nothing that could be reprogrammed from afar. Attackers looking for a backdoor would find only raw data checked by the Series 1's simple deterministic logic. The absence of firmware meant the most common modern exploit. Malicious code slipped into a device's bootloader simply didn't exist here. Engineers also faced the threat of electromagnetic pulse, a real risk in any nuclear scenario. Pre-microprocessor hardware built with discrete transistors and, in early models, magnetic core memory proved far more robust than modern silicon. EMP tests in the 1990s showed that the Series 1 could withstand fields of 10 kilovolts per meter without losing function. Modern commercial servers, by contrast, typically fail at half that intensity. The system's slow clock speeds and lack of dense, high-frequency circuits further reduced its vulnerability. Even when the Air Force transitioned to solid-state storage in 2019, the air gap remained. The new drives carried cryptographically signed, read-only firmware, and the physical isolation was preserved. The core principle endured, a system designed for survivability, not convenience, and built to resist both digital and physical threats. The Government Accountability Office did not mince words in its 2016 audit. SACCS earned a high-risk rating for continued operation, not because of looming cyber threats, but because the system was running out of physical lifelines. Spare parts for the IBM Series 1 had vanished from official supply chains. To keep the backbone of the nation's nuclear command alive, Air Force logisticians turned to unconventional sources, surplus warehouses, private refurbishers, and increasingly, online marketplaces. One procurement officer recalls a power supply module ordered from an eBay seller in 2017. The component arrived with a mismatched serial plate. Bench testing exposed a counterfeit transformer that could not meet electromagnetic pulse hardening standards. The part was quarantined, the vendor blacklisted, and the incident was logged as a counterfeit scare in the Inspector General's annual report. This was not an isolated event. The GAO documented more than 30 separate eBay sellers offering Series 1 parts, each transaction a gamble between necessity and risk. By 2018, the cost for a single replacement I/O card had climbed above $12,000, with lead times stretching past 9 months. Verified source policies were put in place, requiring senior technicians to inspect and test every component before installation, but the bottleneck persisted. GAO analysts warned that as the pool of authentic hardware dwindled, the risk of a single-point failure grew. A single counterfeit module, undetected, could compromise the survivability of the entire launch chain. The logistics strain was no longer theoretical. It was a daily reality, measured in delayed maintenance, emergency procurement plans, and mounting costs. As one analyst put it, you can't air-gap your way out of a broken supply chain. Keeping SACCS alive demanded more than scavenging hardware. The workforce itself became a limiting factor. By 2019, every new technician assigned to the program entered a year-long apprenticeship, paired with a retired IBM engineer or a veteran Air Force programmer. The process was slow and deeply hands-on. Apprentices spent months learning to interpret handwritten wiring diagrams, decode error lights, and diagnose faults with analog multimeters. These were skills that had vanished from most modern electronics training. A senior sustainment official put it plainly: "We're teaching 20-somethings to think like engineers from 1977 because the system won't tolerate shortcuts." This human bottleneck added a hidden premium to every maintenance task. Specialized labor costs rose sharply. In 2015, the Air Force spent $5 million on legacy systems, training, and overtime alone, nearly a third of the total sustainment budget. The apprenticeship program was essential, but it could not reverse the march of retirements. As the last generation of Series 1 experts left the field, each lost technician meant longer lead times and higher risk of error. The financial strain kept growing. By the middle of the 2010s, annual spending for SACCS reached $18 million. Spare parts accounted for the largest share, but labor costs and environmental controls for aging media were not far behind. Lead times for a single replacement board stretched past 9 months. Emergency repairs sometimes required flying in independent contractors, each with their own security clearance and learning curve. The system's reliability now hinged on a shrinking pool of specialists and a budget that climbed every year. The cost of keeping the air gap secure was no longer just technical, it was human, and it was mounting. Stuxnet, discovered in 2010, changed how security experts view isolated systems. The worm slipped into Iran's Natanz uranium plant not through a network, but via an infected USB drive, planted by someone with physical access. The attack showed that even air-gapped machines, systems with no internet connection, can be compromised if removable media or insider actions go unchecked. US Nuclear Command was not alone in betting on isolation. Open-source reports indicate Russia's strategic rocket forces still rely on legacy command hardware, some dating back to the Soviet era, and keep it separated from outside networks for the same reason: to limit digital attack surfaces. This logic has also caught the attention of civilian operators. Utility companies and some airline pilots have experimented with non-networked backup controls, hoping to shield vital functions from ransomware and remote exploits. Across these cases, the lesson is clear: physical isolation can reduce risk, but it does not erase it. Human factors and removable media remain the weak points no matter how old the hardware. Beyond the missile silos, the US Nuclear Command structure relies on multiple, independent lines of communication. Airborne command posts like the E-6B Mercury, known as Looking Glass, stand ready to relay launch orders if ground nodes are lost. Submarine communications depend on very low-frequency signals, which can reach Ohio-class submarines deep beneath the surface, but only at slow data rates and with strict message constraints. These systems operate outside the SACCS envelope, each with its own hardened protocols and physical safeguards. Yet even as new platforms are fielded, persistent gaps remain. The Sentinel modernization program, intended to unify and upgrade these channels, has seen its budget overrun projections rise by 81%. Pentagon reviews point to the complex challenge of synchronizing legacy and next-generation systems, raising questions about whether true end-to-end survivability is being achieved, or if critical seams remain in the nation's most sensitive command chain. Today, as digital threats escalate, the logic behind isolation and simplicity grows harder to dismiss. Floppy disks may invite mockery, but their air-gapped resilience challenges our assumptions about security. The real risk now is believing that newer always means safer. Thanks for watching. Your thoughts are welcome below.